Let's consider a macroscopic object that is moving in a fluid. We will see that such an object will experience a force proportional to its velocity trying to slow it down, and the friction force the object feels while moving in the fluid depends on a property of the fluid called viscosity. So an object moving in a fluid feels a friction force proportional to its velocity, trying to slow it down. And this force depends on a property of the fluid called viscosity. The friction force depends on the viscosity of the fluid. And first of all, when I say a fluid, I mean a liquid or gas. And let's think about a constant, z is equal to a constant plane inside a fluid. So let me clarify here. Fluid means liquid or gas. All right, so I have z is equal to constant plane in a fluid. So this is the z-axis and this is the x-axis. And as you can see, the fluid below the plane exerts a force Pz on the fluid above it. And the fluid above will exert a force minus Pz on the fluid below it. And this force that is in the z direction on the z-axis, that is due to the that is around the z is equal to a constant plane, is called Pzz, and it's actually equal to the mean pressure of the fluid. So the fluid below z is equal to a constant plane exerts a mean stress, that is force per area, Pz, on the fluid above, and the fluid above also exerts a mean stress minus Pz on the fluid below. And this mean stress is actually equal to the mean pressure of the fluid. And there is also a stress that is tangential to the z is equal to constant plane, that is called Pzx, or denoted by Pzx here. And if the fluid is at rest, or moving with a uniform speed, the tangential stress Pzx, so it is due to the z is equal to constant plane, so the first index is the plane orientation, the second index is the component, so it's the tangential component, it's the tangential stress. This is going to be equal to 0. So if the fluid is at rest, the fluid below z is equal to constant plane will not exert a tangential stress on the fluid above the constant z is equal to constant plane, or if it's moving with a uniform speed, it will also not exert a tangential stress on the fluid above the z is equal to constant plane. Now let's think about another scenario where we have a gradient in the speed of the fluid, so that at the bottom level the fluid is in touch with the ground, so it's not moving. The tangential speed ux is equal to 0. However, at the top it's going to have a speed u0, and there is a gradient from top to bottom, where the bottom is denoted by z is equal to 0 and the top is z is equal to L. So I call u the mean velocity of the fluid, and ux, the tangential component, is a function of the distance from the bottom of the container and not time dependent, but it depends on the depth of the fluid. And we have the following conditions: ux, the tangential velocity is ux at z is equal to L, at the top of the fluid is u0, and the x component of the velocity at z is equal to 0 is 0. Now, once again, Pzx is our tangential stress. It is defined as the mean force in the x direction, positive x direction, per unit area of the plane, so z is equal to constant plane, which the fluid below the plane exerts on the fluid above the plane. So basically, Pzx is tangential stress. And to a first order approximation, we see that this tangential stress, Pzx, depends on the gradient of the x component of the velocity, tangential speed. So it is minus a coefficient eta del ux del z. So this is a first order approximation, and we see that this coefficient eta is called the coefficient of viscosity. And eta is defined as a positive constant. It depends on the fluid. And if you look at dimension-wise what eta should be, we have force per area, so kilograms, F equals ma, kilograms meters per second square divided by meters square, that is the dimension of pzx. This is going to be equal to the unit of m, so dimension of m, multiplied by the change in speed per length, meter square, meter divided by second per meter. So we find that this meter will disappear with this meter will disappear with this meter, and then we will have the second disappearing with this second, and therefore we find that the dimension of eta shows us a unit kilograms per meter second. So kilograms per meter second is called poise. So it's called poise. So the viscosity is measured in units of poise, which is kilograms per meter second. And you can see that if the tangential speed del ux del z is increasing with distance, so the gradient is positive, then you will find that the mean tangential stress pzx is going to be negative, which is trying to slow it down. And at the same time, if you look at, for this example, this gradient del ux del z will be equal to, since I have a uniform gradient from z equals 0 to z equals L here, all the way from 0 to u0, it's the change in u divided by the change in z, which will be u0 divided by L, and that's going to be a constant here for this example. And you can see that the mean tangential stress will be then minus coefficient of viscosity u0 divided by L. So for an object, a macroscopic object that is moving in a fluid, it's going to feel a friction depending on its velocity, and the fluid will try to slow down the motion of the object, and the force of friction depends on the viscosity of the fluid. The fluid can be a liquid or a gas. If you have a constant z-plane on this fluid, there is a pressure that is being exerted by the fluid above this plane, and there is also a pressure, mean pressure, that is being exerted by the fluid below the plane to the fluid above the plane. So one is in plus z direction, the other one is in minus z direction, and that is pz. If you call it pzz, that means the stress above the z equals to constant plane z component. So if the fluid is at rest, or if it's moving with a uniform speed, there is no x component of this stress. So above z is equal to constant plane, there is no tangential force that is being applied by the fluid moving below it, because it's either at rest or moving with a uniform speed. So this is due to Newton's laws of motion, basically. F net equals ma, so if there is no acceleration, as you can see, there is no force. So the uniform speed or fluid at rest implies that there is no net force being applied. Now, if the mean velocity of the fluid is actually changing with z, from z equals 0 to z equals to L, the change in the speed will basically imply with z that there's going to be a mean force in the x direction per unit area of the plane. That's called Pzx, the tangential stress. And this tangential stress is proportional to the gradient of the tangential speed, and it's defined as minus eta, coefficient of viscosity, del ux, del z. By doing a simple unit analysis, we see that the unit of eta is kilograms per meter second, or you can say the dimension of eta is m divided by lt. This unit is called poise, and if the gradient is positive, as you can see in this example, del ux del z is positive, the Pzx is going to be negative because eta is defined as a positive coefficient. And basically it implies that the tangential stress is trying to slow down the fluid. And for this particular example, there is a uniform gradient from 0 to u0, from z equals 0 to z equals l. So delta u over delta z is u0 over l is a constant, and therefore the mean tangential stress would be equal to minus the coefficient of viscosity u0 divided by l.